So, now we will open up the lectures on module 2. In module 1 we discussed about the dynamic analysis in general, the basic fundamentals of single degree and multi degree freedom system models, and we found out what are the natural frequencies and mode shapes of different kinds of idealized mathematical model systems. We use different methods, numerical as well as analytical techniques, to solve the equations of motion for a single degree and multi degree, and we understood the necessity of finding out the, let us say, the dynamic characteristics of the systems, as well as we also understood what are the features of introducing damping in a given system and why damping is essential for offshore structures, because we have hydrodynamic damping inherently present in the system. Therefore, it is essential that we understand the response behavior of a damped and undamped system for a multi degree, and essentially we must know that what is the range of the excitation frequency happening or exciting the structure, and what is the natural frequency band of the structural system, and whether the structure is going to resonate for a given loading, and if it resonates what would be the response. So, we understood all of them analytically and numerically and tried to find out them. Now, in this module we will try to apply them for different kinds of problems which are mathematically idealized problems on different types of structures. So, the module 2 will focus on fluid structure interaction. We will also speak about dynamic analysis of different kinds of offshore structures, starting with the fixed jacket structures, gravity platforms, tensionless platforms, articulated towers, and dynamic analysis of offshore structures with perforated members. So, in this module we will take you round that what are the different kinds of mathematical idealization we follow to do dynamic analysis of real mathematical model structures in terms of experiments and analytical. So, in this module we will talk about some techniques where we have used for experimental and analytical studies as applied to offshore structures. We will also talk about some numerical simulations carried out for dynamic analysis of offshore platforms. In addition, we also talk about the response control methodologies that can be applied for offshore structures. One minute, those who have come late, please leave the hall, please leave. Pandiyapan, please leave. So, we will talk about response control methodologies as applied to offshore structures. So, one can see that there are many methods by which response control algorithms are applied to land based structures, but this kind of application is completely novel and innovative. One may wonder that why response control algorithms are not applied to offshore structures, because in overall research as on today, people did not bother to actually apply response control. People only applied their mindset to estimate the responses. So, in this module we will talk about some interesting recent research carried out by researchers available in the literature, where they attempted some response control mechanisms for offshore structures. We will also take you round some important stability analysis carried out for offshore platforms. In all the studies when we discuss, we will also highlight some important recent research ideas and conclusions through various research papers. So, we will apply this for new form of offshore structures. So, we will apply this for new form of offshore structures, and more interestingly we will talk about something called retrofitting of offshore structures. Again this is a new segment where people apply this technique for land based structures, but why retrofitting is essential for offshore platforms, what is the necessity, what are the different approaches did by people, we will also talk about this. So, this module will be very interesting because we will start applying the dynamic analysis principles and concepts for various kinds of offshore platforms as listed in the slide. We will talk about fixed jacket structures, gravity platforms, tension like platforms, articulated towers, and dynamic analysis of offshore structures with perforated members. So, in this lecture we will focus on fluid structure interaction, maybe in the next lecture as well we will focus on FSI. Just to take a brief round what we discussed in the last module very quickly on offshore structures applicable to FSI focus. The majority of offshore structures support the exploration and production of oil and gas platforms. The other major structures generally have deployed other than for oil exploration are essentially for harnessing wave power, because we have got floating devices where people start installing it on the floor of the seabed to harness wave energy, then also to create temporary bases for naval applications. People also design floating platforms. There are of course offshore at ports etc. For tourism development also some of the structures are designed offshore. Therefore, offshore structures can be very briefly classified either by their function or by the geometry. We discussed about this earlier. So, the predominant classification of offshore structure will start from the geometric point of view as far as dynamic analysis is concerned. So, when you talk about let us say dynamic analysis is concerned, it talks about two kinds of structures. One is structure dominated by form, other is structure dominated by function. Essentially offshore platforms are form driven. I can give very classical examples again this head, starting from let us say steel jacket platform, gravity based structures which are essentially concrete, then moved on to guide towers, moved on to articulated towers, single leg AT and multi leg ATs, then we moved on to spar platforms and TLPs, then moved on to FPSO and so on. Talk about structures related to function, we can say drill ships, non ship shaped FPSOs, of course FSOs, and of course now floating FSRUs, floating storage regasification units, because regasification has become a very important aspect in offshore oil production. So instead of transporting the crude oil from offshore to onshore and then wasting the residual material after processing, people started doing the regasification in the offshore platform itself, then transfer only the gaseous part of it. So the remaining residue may not be transported, because transportation cost from offshore to onshore because of the longer length of the pipelines becomes very expensive. So recent studies conducted in Indonesia very clearly show that FSRUs save more than about 40% cost of post processing of oil. So people started moving the idea of post processing from onshore to offshore itself. So people need a very large kind of floating storage and regasification units, which are now coming up in the later stage, and of course semi-submersibles. Though I have not mentioned about jack-up rigs, these are also important concept by form. So the dynamic analysis in both of them categorically divide, because here in these cases where function is important, we work dynamic analysis with a focus on displacements, whereas the structures where it is dominated by form, we work focus on size. So obviously structures which are dominated by form, talked about size, I want to make them rigid, therefore I do the following. I want to make them flexible, therefore I do the following. So when talk about classification by configuration, which we already saw in the last module, based on the configuration they can be classified either bottom supported or floating. From the list we can easily see which are supposed to be bottom floated, which are floating. So just for understanding, bottom support structures can be again classified into two forms, which are either fixed or compliant, because I am talking about the flexibility and rigidity imposed on the structural form. So when you start fixing the base of the structure to the seabed, I will get enormous rigidity because of the fixity offered to the platform on the seabed. When you talk about floating or compliant systems, then we will talk about flexibility introduced in the form itself. So bottom supported structures can be either two ways, one is highly rigid or very highly flexible, or on the other hand fixed and compliant structures. Fixed structures have examples of jacket platforms, gravity based structures for example, whereas compliant type can have guide towers, articular towers, TLPs and spars, etc. When you talk about the next type of configuration, which is the floating type, we already said floating type are also compliant in nature. Then in this case you can have neutrally buoyant type structures like semi-submersibles, FPSOs and monocolumn spars, whereas when you also have positively buoyant type where TLP, and TLP we understand the form is very interesting because the buoyancy enormously exceeds the weight of the platform. That is the fundamental catch here in the design as far as TLPs are concerned. As far as TLPs are concerned, buoyancy force enormously exceeds the weight of the platform. On the other hand, if the weight of the platform is enormously low, this has many advantages. The installation becomes economical, material cost is low, what we call as capex. capital investment towards initial form is low, reinstallation or decommissioning becomes simple, and because of these advantages it can go for deep to ultra deep waters. So that is the innovative form as far as TLP is concerned, which is a positively buoyant type structure, whereas neutrally buoyant you have semi-submerged, which depends upon the draft at which it is being installed, and of course FPSOs and monocolumn spars. So we will speak about fluid structure interaction now. Do you have any questions what we have in the discussion just now before we start introducing you to the fluid structure interaction problem? Any questions? Okay, we will talk about FSI. Fluid structure interaction plays a very important role for structures placed in the flowing fluid. For example, if you have got a fluid path where you place a structural member in the path of the flowing fluid, then the structural interaction with that of the fluid flow plays a very important role. You see what are the factors which will affect this? The presence of structure essentially alters the fluid flow field in the vicinity of the member, that is very important. So one may wonder how the influence of fluid flow field in the vicinity will affect my dynamic analysis. To understand very briefly, let us say I have a member, I am drawing the plan. Usually offshore structures are circular in diameter and they are hollow, and this is my fluid flow field. The fluid flow field, so it alters the characteristic of the field in the vicinity of this. So it influences many factors. It can create vortices. Vortices are nothing but forces associated with different frequency contents. It can create of course oscillations parallel to the flow and normal to the flow. Can also create blockage, can also create shear. It introduces a new region which is called wake region. So the interference in a single cylindrical member, and of course orientation of the member, whether you place the axis of the member parallel to the flow or normal to the flow, and of course the flow field. Whether the flow field is uniform or shear type, depending upon the variety of factors influencing the flow field on the member, fluid structure interaction becomes interesting and important. And therefore how this affects dynamic analysis is very simple. In the left hand side of equation, if you see, let us say mx double dot plus cx dot plus kx is f of t, that is my classical dynamic, let us say the equations of motion for a given member, maybe single degree or multi degree. Let us quickly understand which are the parameters here which will get influenced by the fluid flow vicinity in the member. As I said, blockage is one aspect which can affect the force acting which depends upon the diameter of the member and series of members in the row. So it will affect the mass, and blockage or oscillation frequency sometimes will also affect the submergence effect, which will again affect the mass because of the variable submergence, and the shear in the region or the shear flow will affect the direction of forces acting on the member, so f of t will be affected. The orientation of the member can create vibrations along and across, which will offer again forces in 2-dimensional state. Vortices induced frequencies will cause secondary vibration, which will affect omega, which is again a function of k and m of the whole system. So fluid flow with an interference to a structural member, which we call as fluid structure interaction, can influence many parameters in your equations of motion. In addition to that, if the structure is compliant by form, k will be affected because of the FSI, and of course because of the submergence effect and because of variance of k and m instantaneously, c will be also affected. So all parameters especially will get affected if you have any structural member interfering with the fluid flow regime in any uniform field or any turbulent field as well. So FSI becomes a very important parameter, because we should understand how fluid structure interaction will influence the dynamic behavior, response behavior of a given structural member in the given regime of fluid flow. That is what we are trying to look at it. How this is taken care of, we will talk about that, because I said all these parameters will get transformed directly or indirectly in the dynamic analysis. How they are getting transformed is what we will see slowly as we look into different kinds of platforms, but let us try to understand what are these and what do you mean by them and how do we compute them approximately. We must know this, okay. That is what we are looking at here. So therefore the degree of compliance offered with the structure adds further complexity. For example, if the member is fixed to the bottom, if the member is infinitely long, if the boundary conditions have no effect on the fluid flow, then the behavior of the member is different, or the interference of fluid on the structure in the vicinity is different. If the member has a finite length with the member's ends closed and the member is closer to the submerged region or closer to the free surface, then the boundary effects will play a role on this, and therefore if the member is also not fixed but floating, as in the case of TLPs etc., then in that situation then the compliance offered by the member will again introduce further complexity to the fluid regime or the fluid flow regime in the vicinity of the member. So not only the member dimension, not only the member orientation, but the member location and the member fixity will also affect the characteristic or influence the characteristic behavior of the member in the given fluid flow regime, which we call as fluid structure interaction. So even though structures remain flexible, for example TLP, as the members move when the force is acting on the member, the structure is considered to be, or the members are considered to be flexible in certain degrees of freedom, because it has 6 degrees of freedom, whereas all the 6 degrees are not compliant, only few degrees. For example surge, sway and yaw motions are compliant, whereas heave, roll and pitch motions are not compliant, they are stiff degrees of freedom. So in few degrees of freedom it is compliant, however even in the stiff degrees also dynamics becomes important, because in compliant degrees response will become important, in stiff degrees forces will become important, okay. That is how we will, when we have a structure fixed member or member fixed to the support, forces are becoming important, because then response will be very minimum. For example gravity based structure or fixed jacket structure. So when you have got a structural system or a member whose dimensions are related to the flow field and the boundary conditions impose fixity on the member, then forces on the member, stresses on the member becomes very important, therefore fatigue plays a very important role. When we talk about compliant structures, then response becomes important. So for example a compliant system like TLP, where certain degrees are fixed, certain degrees are compliant, both are important, okay. So we are not looking at the deformation capacity, it is very important to understand what is the difference between the response and deformation capacity. Let us quickly look at this now to understand the difference between these two. Suppose I have a structural member which is compliant, maybe a buoyant leg structure BLS. Let us say for example, let us consider a buoyant leg structure which is BLS, which is nothing but a cylinder which is anchored to the seabed using tether. For different purpose they have been used. Okay. For example, it can be a simply floating point observers, point buoys, etc. So under the wave action, the structure or the member keeps on oscillating. So I get x of t in a specific degrees of freedom, let us say x1 of t, which is surge motion. This is the response of the system. For example, the maximum response of the given wave height and wave period at one instance goes to, let us say, 2.5 meters for example. Whether the member or the fittings attached to the member can sustain this response is the capacity of the member. In the dynamic analysis we are not looking at this, that is design. In dynamic analysis we are looking only at this. Okay, that is what I am saying here. It is not the deformation capacity of the member. We are not looking at the deformation capacity of the member, we are looking at the response of the member. They are different. Of course, if the deformation capacity exceeds the response of the member is safe, otherwise the member will get into post ductile behavior depending upon the material characteristics, etc. That is the design part of it. We are not looking at that at all in the dynamic analysis. Remember this, they are not combining these two. We are looking only at the response feature of this, we are not looking at the capacity of this. So it is very clear, deformation capacity is not looked. Therefore, material characteristics will not play a major role in dynamic analysis at a primitive level. Then one can say, how can you include the material characteristics also on the dynamic analysis? I can say you do non-linear dynamic analysis, where non-linearity can come from many sources. One of the sources what we have in the offshore structural system is f of t. The forcing function itself can be a non-linear function. The remaining non-linearities can come from large deformations, large displacements, and of course the material characteristic, etc. So if you want to include this behavior in the dynamic analysis, then I should do non-linear dynamic analysis. If I do not want to include them, I simply say dynamic analysis where I am looking only at the response and not the capacity. Okay, that is what this last point in the slide means, that we are not looking at the deformation capacity, but we are looking at the response. Is that clear? So FSI becomes interesting because when we talk about a steady flow, then steady flow may be in the form of a current or a vertical shear, but in the real sea state structures experience large oscillating forces in the flow direction, as I just now showed you what are the factors affecting the members in the vicinity of the fluid regime. When the structures are placed in the flowing fluid, then the flow pattern of the fluid itself is altered. That is very interesting. As I showed you here, the uniform flow can get altered and diversified. So the flow fluid itself, the flow pattern itself will get diverted or changed because of the presence of the member, depending upon how large is the member, how many number of members are kept in series and parallel, and so on, what is the spacing of the member, etc. So the flow direction or the flow pattern itself will get changed, and of course whenever a member is subjected to an action given by the waves, for example lateral forces, the member will always invoke reaction to it, what we call restraint forces. Okay, it is an excitation force, is the force given by the external agency, in this case a wave train. So the member will develop an opposing force to it, what we call restraint force, which depending upon the material characteristics of the member, the dimension of the member, the boundary condition where the member is fixed or floating, etc. So these restraints developed in the fluid medium will be actually essentially responsible for maintaining the position of the member. If the restraint force are much less than that of the excitation force, the member will start moving. If the restraint force are much higher than that of the excitation force, the member is considered to be stiff, it will not move, the response will become very low. So the restraint are developed in the fluid medium to maintain the position of the structure. It has nothing to do with the reaction to the forces, it is actually invoking the position fixity of the member in a given fluid regime. Why? When the fluid attacks or let us say acts on a given structural member, the fluid field around the member try to disturb the position of the member. So the restraint force on the member are developed only to counteract this, okay, that is what we say indirectly as fluid structure interaction. On the other hand, structure is not exposing any force back on the fluid regime, it is only developing restraint forces which are essentially responsible to keep the member in geometric location and position. Is that clear? So on the other hand, in simple terms, waves try to push the member, members do not want to move, they oppose or generate restraint forces. So this is actually nutshell happening in a FSI concept in a given vicinity of the member. Now the question is, before the member and after the member vicinity, the train is as normal as it is, okay, it is only around the vicinity we are bothering. Is that clear? So forces acting on the structure in fluid medium can be further classified interestingly into two parts. One is what we call as a drag force, which acts in line with the direction of flow. The other is what we call a lift force, which is transverse to the direction of flow. It categorized into two parts, we all know this. So the coefficients which are responsible to estimate these forces are nothing but CD and CL, which is referred in the literature, and we all understand this. So interestingly, I have a question for you, list the factors that influence, we already spoke about this in the first module, that influence CD and CL in the loading of offshore platforms. So this is an exercise for you just to find out what are the factors which will contribute to the variation of CD and CM. I can just give a clue for you, CD and CM is affected essentially by marine growth, roughness, presence of current, blockage. I mean there are many factors. I want you to just look into this and see what are the factors which influence these coefficients, which are essentially force coefficients, because when the member is interacting with the environment in case of fluid regime, as I initially said, the members develop restraint forces just to keep the members in position. These forces are generated in two formats, one is in line with the fluid flow, other is transverse to the fluid flow, what we call as drag and lift forces. So remember, drag and lift forces are essentially the restraints developed by the member to counteract the action of the wave or the horizontal forces on the member, essentially to keep the member in position. So drag force can further be classified as components having higher and smaller frequencies, because drag forces will have components of different frequency bands. It can have higher and smaller frequency components. Why we are interested in dynamic analysis in frequencies, because we are talking about the frequency content of the force which is generated because of the excitation phenomena and the frequency because of natural characteristic or the dynamic characteristic of the system itself. Okay. So drag has both the components which is having smaller and higher frequencies. These components of course will be a function of geometry, we already saw that, and the flow conditions which you are seeing now. So these are two ways, it depends on the geometry of the structural system as well as the flow conditions also. Of course, if you talk about lift forces contain oscillatory components with multiple frequency bands. Okay. So very interestingly, when you talk about these two kinds of forces in transient and steady state response, there are two kinds of response we have seen in dynamic analysis for a given member or a given structural system. So initially it can be a transient response, and then of course it can be a steady state response. We already seen the categorically the difference between the transient response, steady state response, single degree freedom system analysis in the last module. So sometimes interestingly even the transient response sector can also become important. This can cause what we call ringing response and springing response. Essentially on complaint structures. Therefore, interestingly if you have a lift force which is having multiple frequency bands, it is important for me to understand the frequency band and the amplitude of these forces. Okay. So not necessarily that multiple frequencies may have a lower content, but since the frequency content is predominantly representing my response function, I can always have resonance even in the transient state itself. Okay. So we will talk about this later about the ringing and springing responses in complaint structures like TLPs and spars. So even the transient response sometimes becomes very important or phenomenally important in certain cases where we talk about the responses under large band of frequencies with lower amplitude or small band of frequency with higher amplitude, which can be otherwise not important in dynamic analysis, but sometimes even this can excite the platform to a dangerous level of XFTs. So lift forces can also contain oscillatory components which are also important for us. So drag contains higher and smaller frequency components which are essentially function of geometry and the fluid flow conditions, whereas lift force contains variety of oscillatory frequency components. We talk about the fluid structure interaction when the wave train is hitting a member on the downstream side. On the downstream side, flow will return to its unaltered condition after it interacts with the member. After the flow past the member, so on the downstream side the flow returns to its normal in an unaltered state after it passed the member. There are reasons for this why this flow which has been disturbed or the flow field which has been disturbed because of interference of the member returns to its normal. There is a reason for this. The reasons are it is depending on the viscosity of the fluid and of course the damping present in the system, not the structure. The system means hydrodynamic damping present in the water body. So because of these two reasons, even though the fluid flow is disturbed turbulently in the vicinity of the member, after it passed the member on the downstream side it becomes again normal. Okay. The reason is viscosity of the fluid as well as damping present in the system. Now let us look at this region where my fluid flow is significantly altered or disturbed. So the region just behind the member, this is my forward member, this is the backward direction. The region just behind the member is what is called wake region. This is a wake region. Okay. Interestingly, the wake region has a very special characteristic. We will see that quickly in the next slide. In the wake regions, interestingly, there is one-to-one relationship between the extent of wake region and the restraint loads. Depending upon the restraint loads generated by the member, what is the extent beyond which the wake region will not be present is dominantly controlled by the forces generated by the member. There is a one-to-one correspondence of this, and interestingly the fluid structure interaction in the wake region therefore becomes deterministic. It is not very complicated, it is very simple because it depends purely on 1:1 relationship of the restraint force generated by the member or the cylinder. So the frequency content of wake region has same as that of the restraint loads. If the restraint loads have a frequency band, for example from 15 to 25 hertz, wake region will develop the frequency on the same exactly in the same range. It means wake region is actually a response reflection of the disturbance caused by the member on the fluid flow. Okay, it is on the downstream side. Now the wake region alters the fluid flow significantly. Let us see how does it do. If you look at the flow regions or flow regimes in uniform flow, if you keep the axis of the member normal to the flow direction and the flow is assumed to be no turbulence and boundary effects are neglected, then in that case there are 4 kinds of flow regions which we can identify. One is what we call laminar flow, when the Reynolds number lies between 0 to 40. The flow is called as subcritical, supercritical and transcritical depending upon the value of Reynolds number varying from 40 to 5 10 power 5. This 5E05 is nothing but 5 10 power 5. Okay, Reynolds number varying from 40 to let us say 5 10 power 5 is what we call subcritical, and supercritical varies from 5 10 power 5 till 7, and the number is more than 7 10 power 5, we call the flow regime as or flow region as transcritical region. Depending upon solely on the Reynolds number, we can say that the flow conditions can be again defined for the different regions as we see in this table. For example, the flow is purely laminar, there is no separation of flow, which will result only on drag forces on the member in the direction of flow. It means if a Reynolds number is lying between the range of 0 to 40, the flow will remain laminar and no separation will occur, and dominantly drag forces only will be present, or drag forces are the restraint forces generated by the member because of the FSI acting on the member. Is that clear? If the Reynolds number varies from 4 to 40 to 5 10 power 5, if the flow region is subcritical, then we generate or we see what we call broken streamlines. Therefore, lift forces present in this region will depends upon the Stokholm's number, and it will have the steady drag force component plus smaller oscillating drag forces which will oscillate at the double frequency of lift force. So there will be 2 components distinctly seen in your response or in the force generation. One will be of course the steady drag force, the other will be a drag force which will be oscillating at a frequency as that of double of the lift force itself. Okay. So look at the supercritical region, we have got ill defined vortices generated in this region, drag forces decrease rapidly in this region. Of course lift forces and drag forces will be seen at very high frequencies in this region. If the flow region moves to transcritical, vortices will be present dominantly and the flow will become turbulent, and the forces on the cylinder generated will be as similar to subcritical regions, where the lift force again depends on the Stokholm number, and the drag force will have 2 components, one will be a steady drag force and other will be a drag force occurring at a double the frequency approximately as that of the lift forces. So depending upon the member interfering the flow region, depending upon the location or the orientation of the member, the axis of the member or the axis of the cylinder is now kept normal to the flow direction, and of course you ignore or you do not consider the turbulence in the flow field and you do not consider the boundary effects at all, it is a free boundary. In that situation the flow region can be divided into 4 components depending upon purely on Reynolds number. I can easily estimate the force on the cylinder as either a drag force or a lift force or a drag plus lift at different frequency bands depending upon how the member interferes with the flow field. Looking forward further, if we look at the vertical cylinders in uniform flow, the vertical cylinders experience loading from the flowing field. Again the fluid structure interaction will be again defined by the Reynolds number for the cylinders, provided the cylinders are considered to be infinitely long, smooth and fixed. So if you have got infinitely long, smooth and fixed cylinders, then you can always estimate the response of these members in FSI region purely based on Reynolds number only. The cylinder roughness and fluid turbulence reduce the boundary value of course on either side of the supercritical region. If the length of the cylinder becomes finite, then the problem will translate to 3D aspect of the fluid flow. If you got a finite length of the member, then the fluid flow aspect of the fluid structure interaction problem will get into a 3D mode. So the ends of cylinders will affect the drag and lift coefficients, as we just now saw CD and CL. Therefore you can always say the factors influencing CD and CL can also depend on whether the ends of the cylinder is finite and it is closed. And of course most importantly, they are location dependent of the cylinder, where the cylinder is lying. The cylinder is closer to the boundary, the closer to the free surface, etc. Location dependent. And vortex shedding pattern will also be affected by the presence of cylinder in the fluid free region. So let us look at this figure or the table, then considerably this figure. If you look at the reduction in velocity occurring because of the interface of the member on the fluid region, you can divide this region into 3 as 1, 2 and 3. The reduction of velocity takes place from 1.7 to 2.3, whereas it can vary from 2.8 to 3.2 and further reduce from 4.5 to 8.0 depending upon the regions of 1, 2 and 3. In the region 1, where the reduced velocity takes place from 1.7 to 2.3, there is what we call symmetric shedding, and therefore only inline oscillation will be present. Look at the vibration problem of the cylinder. The cylinder is expected to oscillate only inline direction, that is on the flow direction only, if the reduction of velocity takes place 1.7 to 2.3, whereas if the velocity reduces very high as 8, then predominant vibration will be in transverse direction. Okay, that is very important. So if you start reducing the velocity of fluid flow because of interference of the member, because of its smoothness, because of its fixity, because of its location, because of its length, because of the boundary conditions, etc., as higher the velocity keeps on reducing, the characteristic of vibration will transform from inline to transverse. Okay. So interestingly, this inline vibration which is happening at a reduced velocity of 4.8 to 8.0 is what we call figure 8 motion. The structure will start oscillating in a characteristic of 8 geometric shape. This is called figure 8 motion. So inline vibration will also be present at a frequency twice as that of the transient vibration. So the frequency content of transverse as well as inline both will be appearing in case when you have a reduced velocity of 4.5 to 8.0, and this occurs essentially because of vortices shedding. If you look at flow in deep waters, the flow is not uniform with the depth, it varies. Positive shear will be mostly seen, velocity will be greater than that near the surface as you go deeper and deeper. When vertical cylinder is in a shear flow condition, then generate what we call 3D regime in the flow field. So if you look at the wake region, interestingly, this is my cylindrical member, this is my cylindrical member, this is my flow direction, which is my flow direction. If this is my flow direction, on the upstream side the flow is downward, on the upstream side the flow is downward, whereas on the downstream side the flow is upward. Okay. So the presence of member alters the flow field in the wake region like this. As I just now said, behind the member is what we call as the wake region. So on the upstream side the flow is downward, whereas on the downstream side the flow is upward. So if you look at the whole problem like this, what does it do is the member actually shears off the flow field. Okay, shearing is nothing but if we have any member or structural member where the force is acting like this, we call this as a shear force, is it not? So the presence of member in this case actually shears the flow field, you can see that. So one way it is downward, other way it is upward. So this is what we call as the flow is sheared off in the upstream and downstream side. So the shear flow effect reduces the pressure coefficient at the top of the cylinder, whereas at the bottom it increases the coefficient. So in the cylinder itself, at the top the pressure coefficient decreases, whereas at the bottom it is increasing. So there is a differential pressure set to the cylinder length itself. The coefficient of course changes with the strength of shear present in the fluid flow. In the uniform flow, cylinder will show vortices at the same frequency over the entire length of the cylinder if the flow is very uniform. Of course, in the shear flow the frequency changes continuously. Any questions here? We have few minutes, take it forward. I think I have one or two more slides. I think I will do this in the next lecture.